Good afternoon, everyone. Today we'll be talking about circular motion. In order for something to travel in a circle, there has to be a net force acting on it. This net force is called centripetal force. That force is perpendicular to the velocity that is moving, which is tangent to the circular motion. Without the centripetal force, the object would move tangent to the motion. That is due to Newton's first law, which states that the object will continue going in the direction that is going unless a force acts on it.
Take for example a tractor turning. In this example, the centripetal force is the force of friction acting on the tires. Notice that the tire is perpendicular to the circular path, and the force is directed towards the center of the circle. The acceleration that causes a particle to revolve around the center is called the centripetal acceleration, denoted A sub c. A sub c equals v squared over r. Because centripetal force is a net force, it is equal to mass times acceleration, in this case centripetal acceleration, meaning our centripetal force equals mass times velocity squared over radius. Notice that the conditions must be just right to allow for a safe turn. If the tractor is moving too fast or turns too sharply, causing the turn radius to shrink, or if the coefficient of friction is too low, for example on an icy road, the tractor will continue on in its current direction and won't be able to follow the circular path. We know that a particle in motion's velocity is calculated as its change in position over time. We also know that the length of a circular path is pi times the diameter, or 2 pi times the radius. This is known as the circumference. The time it takes for a particle to travel the full length of the circumference is called the period, denoted by a capital T. Using this knowledge and knowledge of the mass of a particle or object in uniform circular motion, we can derive the centripetal force acting on that particle or object. You'll notice at the end of the clip that if we already know the centripetal force exerted, we can predict the period. We just need to swap f sub c and t squared to get t squared equals m times 4 pi squared r over f sub c. We can also observe that mass appears to be directly proportional to the square of the period, meaning that as mass increases, we can expect our period to increase. Graphing the data should produce something like this. In this experiment, our constants were radius and centripetal force. Prior to any trials, the spring was measured using a force meter and adjusted so that when the bob attached to the spring was extended to 18 centimeters from the shaft, the spring was pulling with 7 newtons of force. Our independent variable was mass. We measured the initial mass to be 0.3752 plus or minus 1/10,000th of a kilogram. Each trial, a specified amount of weight was added to the bob to increase the total mass, capital M. We increased the mass by 50 grams for trial 2 and by 25 grams per trial for 10 subsequent trials. For each trial, we first increased the speed of the arm until the radius was 18 centimeters. Then, we recorded the time it took for the bob to complete 30 revolutions at 18 centimeters. We divided this number by 30 to get our average period. After obtaining our results, we added an additional column for t squared to be able to compare our data against our theoretical calculation using the previously derived equation. We know t squared equals mass times 4 pi squared r all over f sub c. On a graph, mass will be our x-axis, t squared our y-axis, and our data will have a slope of 4 pi squared r all over fc. Substituting values, we get s, our slope, equals 4 pi squared times 0.18 meters all over 7.0 newtons, which is approximately 1.0. This value is our theoretical slope. The t-squared calculation compounded the uncertainty from our stopwatch measurements. We can account for this with the following equation. The uncertainty of t squared equals 2t times the uncertainty of t. Our uncertainty of t is known to be 0.01 seconds. We plotted t squared over m and discovered a linear relationship consistent with our hypothesis. Using worst fit lines, we found the uncertainty in the slope to be 1/2 the maximum slope minus the minimum slope, which came out to approximately 0.3970, meaning our average slope was 0.6274 plus or minus 0.3970. How does this compare to our theoretical slope? Using a percent difference analysis, we found our experimental slope to differ 47.214% from the theoretical. Well, what does this tell us? Primarily, it tells us that we did something consistently wrong during the experiment, and that in a real-world setting, these results would likely be thrown out. Looking at the uncertainty in the slope, we see some pretty large deviations. It's likely that we were either stopping the stopwatch at the wrong time or not spinning the apparatus properly. It's also possible that our initial force measurement was incorrect. However, it would have had to have been 1.5 times the appropriate value to achieve this behavior, which seems unlikely. Overall, we were happy to see a direct relationship, even though our results were flawed.